If you've built or deployed a retrieval-augmented generation system recently, you've probably run into the same frustrating pattern. You tweak the retriever, you tweak the generator, you add a self-reflection step at the end, and you're still chasing hallucinations, missing context, or brittle reasoning. The reason is simple. Most RAG pipelines are optimized in isolation. You treat retrieval, evidence structuring, and answer generation as independent stages. But when the retriever pulls in sparse or misaligned chunks, the generator has no choice but to work with what it's given. Fixing the final answer doesn't fix the root cause. That's exactly the problem GRAGRAG solves. It's a new framework that treats a RAG pipeline not as a linear assembly line, but as a computational graph where evaluation feedback propagates backward to adapt multiple components simultaneously. Instead of just rewriting the final answer, GRAGRAG uses a structured critique to update the prompts of upstream agents like the retriever or graph constructor, iteratively at test time. And it does all of this without touching model weights. Let's break down how this actually works under the hood. GRAGRAG models the entire RAG workflow as a directed graph. Each node is an agent or a data artifact, and each edge represents a computational transformation. The magic happens in the feedback loop. After a forward pass generates a candidate answer and its supporting evidence, an evaluator agent steps in. It doesn't just say good or bad. It produces structured, natural language feedback that pinpoints missing causal links, weak reasoning chains, or irrelevant context. This critique is then fed into a prompt optimizer, which translates it into concrete, actionable updates for one or more adaptive agents. The pipeline runs again with the new prompts, and the cycle repeats until the evaluator signals satisfaction or a maximum iteration budget is hit. The framework is highly modular, and the researchers evaluated it across two fundamentally different retrieval paradigms to prove its generality. First, flat vector retrieval. Here, documents are segmented into overlapping chunks, and a retrieval agent uses an IRCO-T-style strategy to iteratively generate subqueries. It combines dense similarity search via FAISS with lexical matching using BM25, dynamically choosing the best retrieval strategy based on the context gathered so far. Second, graph-based retrieval. This pipeline extracts entities and relations into a structured graph, runs Leiden community detection to cluster related concepts, and generates natural language summaries for each community. In both setups, the evaluator's feedback doesn't just tune the generator. It actively reshapes how subqueries are formed in the flat pipeline, and how entity relation types are prioritized during graph construction in the graph pipeline. Over successive iterations, this feedback-driven adaptation effectively induces a task-oriented ontology, steering the system toward the exact information needed to answer the query. Now, let's talk about the results, because the numbers here are genuinely compelling. The team tested GRAGRAG on SQLITY and QMSUM, two rigorous query-focused summarization benchmarks. They compared full cross-component adaptation against a strict one-step refinement baseline, where only the final answer generator is updated. The difference is stark. Across both retrieval paradigms, GRAGRAG consistently outperforms the baseline, securing a 12 to 15 percentage point net preference margin in pairwise LLM-as-a-judge evaluations. They validated this with position consistency checks to eliminate order bias, applied two-sided binomial sign tests for statistical rigor, and confirmed alignment with human annotators. And here's the efficiency kicker. Most of these gains materialize within the first two refinement iterations. The system naturally converges, using an early stopping mechanism that prevents unnecessary token burn or overspecialization. The refinement dynamics tell an even more interesting story. As the system iterates, response length increases initially but quickly stabilizes. Lexical density climbs steadily, Rouge 1 scores improve monotonically, and topic entropy decreases. That last metric is key. It measures the Shannon entropy of topic distributions across responses, so a decrease means the system isn't just generating more text. It's generating tighter, more focused, and more coherent responses. The feedback loop is actively pruning noise and reinforcing relevant signal. From a practical standpoint, the computational overhead is surprisingly lean. The cross-component adaptation adds roughly 10% to inference time and increases token usage by about 10%, primarily due to critique processing during prompt updates. The vast majority of runtime is still spent in the forward pipeline, which remains identical across systems. This proves that coordinated prompt adaptation is a lightweight, high-leverage intervention that doesn't require heavier models or massive parameter updates. So why does this matter for the broader AI landscape? Because it flips the script on how we think about agentic RAG. We've spent years treating retrieval, reasoning, and generation as separate optimization problems. GRAGRAG demonstrates that evaluation signals produced at the final stage are incredibly valuable if you route them upstream. By allowing downstream critiques to reshape upstream decisions, you align the entire pipeline toward a shared objective. It's a shift from static one-pass pipelines to dynamic feedback-driven systems that adapt in real time. If you're working on modular RAG architectures, multi-agent reasoning, or prompt optimization, GRAGRAG offers a clean, reproducible blueprint. It shows that you don't need to fine-tune weights or rewrite your entire architecture to squeeze out reliability. You just need better coordination. The future of RAG isn't about bigger context windows or more complex routing logic. It's about closing the feedback loop. And frameworks like this are exactly how we get there.